Audio Jungle.
Hi everyone. In this video, we are going to talk about stack and heap memory allocations. So usually people often think that when they do the programming in a certain programming language, they often think that why do we have to worry about how the operating system actually does the memory management, right? All we need to understand is the programming language concepts, the syntax of the particular programming language, and the features in the language. That is more than enough to solve any problem in the programming, right? Why do we have to understand how the operating system works internally? But I'm telling you, it is really important to understand the internal details of the operating system, especially when you code in system level programming languages like C, C++, or Rust. Because if you understand the details of how the operating system manages the memory, you can actually write some efficient program. So that's why this video is all about how the memory management actually works in terms of stack and heap allocations. So before we get into the actual topic, we first need to understand what is stack, what is heap, and where it actually sits in your computer, right? So basically in your computer, you have two different types of storage. One is RAM. So RAM is what we call it as memory, and another one is disk. So disk is what we actually call as storage. So when you execute a program, you actually have to declare some variables, you declare some functions, and also you store some value temporarily during the lifetime of that application, right? For some kind of a computing or calculation purpose. And that those kind of values usually get stored in the RAM. And when you close the application, the data in the RAM will be wiped off. So that's why we call it as RAM is actually a temporary memory for your application to execute. But in case if you want to persist some data permanently, then you go for the disk. So even after you close your application or even after you shut down your computer and come back, you want to see some data, right? It could be either your user preference, user specific data that you store in your computer. Even after you close the application and open it back, you want to see the data there. So that's where we have to use the persistent disk. It could be either the disk that comes along with your computer, or it could be an external disk attached to the computer, or it could be a persistent disk in the cloud. So now the stack and heap memory allocation actually works in the RAM. It's actually part of the RAM. So in this video, we are going to focus on the stack and heap memory allocation, which is part of the RAM. Now in the programming language, we actually have two different types of memory. One is we have static memory and we have a dynamic memory. So static memory usually gets allocated in the stack and dynamic memory usually gets allocated in the heap. And the static memory we can also call it as value type, and the dynamic memory can also be called as reference type. So we are going to see how the static memory actually works and what exactly is static memory and dynamic memory, and how the static and dynamic memory gets allocated in the stack and heap. So that's what we are going to see in detail in this video. Now let's consider a simple piece of code. We actually have a function and we declared certain variables within the function. Okay, and let's see how these variables gets allocated in the stack memory. Now so if you look at this function, right, we have three variables declared here. We have an integer variable and it holds the value of 10, and we have a float variable and it holds certain value, and we also have a character array which has 3 items in it. Now this is what we actually call as static memory. And why we call it as a static memory? The reason that we call this as a static memory is just by looking at this code, you can actually understand how much space is required for this function to execute. So let's try to calculate. Let's take the first variable, which is of data type integer, and we know how much space is required for a typical integer variable. It is actually 4 bytes. 4 bytes is required for the integer data type. Now the next variable is float, and float also takes 4 bytes of data. And now the third variable is character array. So usually each character actually weighs 1 byte, and we have 3 items in the character array. So this needs 3 bytes of data. Now totally, this function needs 11 bytes of data for the execution. right? It needs to allocate 11 bytes of data in the stack. Now the thing is, the compiler actually knows how much space is required for this function to execute ahead of time, and that's why we call it as a static memory. Since the compiler knows this ahead of time, the compiler actually inserts the necessary instructions into the code when you compile the code into the intermediate language or into the machine language. So the compiler inserts necessary instructions to allocate and deallocate the memory. Since the compiler already knows the size ahead of time, that is actually possible with the static memory. Now let's see how this static memory gets allocated in the stack. So now if you look at the stack is actually a linear or a contiguous block of data. And from this diagram, maybe you can actually consider each block is representing 1 byte of data. Okay, and we call this as a stack because it actually follows the principle of last in first out. So whichever items that you inserted into the stack recently, that would be the first item that you can retrieve from the stack or you can remove from the stack. You cannot actually insert or remove any items from the middle of the stack. Now stack usually also has a pointer which actually points to the recent available space in the memory. So when you declare some variables, it actually allocates some memory in the stack and then it moves the pointer, the offset, into the next available space in the stack. Now let's see how these variables gets allocated in the stack. Now when you execute the program, when the program execution actually comes to this particular line, you declared a variable of data type integer. So we have to allocate some space in the stack for this integer variable. And we know this integer variable actually takes 4 bytes of data, so it actually blocks 4 blocks in the stack for this particular variable, and then it actually moves the pointer to the next available space. And then it reaches the second line. So here we need to declare a float variable, and again it takes 4 bytes of data, so it again blocks 4 bytes of data in the stack. And then it actually moves the pointer to the next available space. And similarly, when it comes to the third line, again it needs 3 bytes of data, so it takes 3 blocks of data in the stack and moves the pointer to the next available space. Now when the program execution completes, when the function is completed the execution, when these variables goes out of the scope, the memory that gets allocated in the stack will automatically be deallocated because compiler would handle that scenario here. So, and again, as I already told you, the memory will be deallocated in the reverse order. First, it will deallocate the character array, and then the float, and then the integer. So this is how the static memory actually works, and this is how the static memory gets allocated in the stack, basically. Now we are going to see how the dynamic memory works and how the dynamic memory gets allocated into the heap memory. Now let's see another simple piece of code here. So in this code, we actually have a function which have a variable called hash map. So the data type of the variable is hash map. So we declare the variable and we initialize the hash map. So in the previous example, we actually have some variables like integer and float, but in this case, we have a hash map. So this is what we call it as dynamic memory. And the reason we call this as a dynamic memory is just by looking at this code, we cannot understand how much space is required for this function to execute. The compiler do not know the space required for the function ahead of time. Because now we just initialized the hash map, we haven't added any items into the hash map. But imagine during the course of the function execution, at some point of time, some items might get added into the hash map, which we don't know during the compile time. And also you can actually make a remote API call, and based on the API call's response, you can populate the items into the hash map. Or you can make a database query, and based on the database response, you can populate the items in the hash map. So unlike an array, when you initialize an array, you actually either give the size of the array or you initialize the array with some fixed number of items, which cannot be expanded or shrink dynamically. But in case of hash map, you actually can expand the hash map. You can add more number of items dynamically, and you can remove the items dynamically from the hash map. So because of these reasons, we call this as a dynamic memory, and we cannot allocate this memory into the stack. The reason that we cannot put this into the stack is we all know that the stack is following the principle of last in first out, which means you cannot insert or remove any items from the middle of the stack. Now, even if we just imagine if the compiler tries to allocate the hash map into the stack, it just assumes some maximum size for the hash map, let's say 10 bytes of data, and then if it allocates the hash map into the stack like something like this, and then it moves the pointer here. Now after this line, you may have some kind of a line like this. You are declaring another variable of data type integer. Now it needs to allocate some portion of memory in the stack for the integer. Let's say it allocates 4 bytes of data in the stack and moves the pointer to the top. Now after this line, if you try to add some items into the hash map, what will happen? That's where the actual problem comes in, right? Because you cannot put any items in the middle of the stack. So you cannot expand or shrink the hash map if you allocate the hash map in the stack. So this is where heap comes into picture. So with the heap, you can actually randomly allocate some section of memory in the heap where you have enough opportunity to grow or shrink. That's the main point about the heap. So maybe the heap memory would look something like this. And when you declare a new dynamic memory, you actually allocate some section of memory in the heap, and where you actually have enough opportunity to grow, and actually you put the reference, the address of the heap memory into the stack. So that's how usually it works. So now let's see how this program execution happens and how these variables gets allocated into the stack and heap. Now when you execute the program, when the execution reaches this particular line, so here we are actually declaring a variable called the hash map names, right? So now at this point of time, as I already told you, it actually for the reference type variables, it allocates a section of memory in the heap, and then it stores the reference of that heap address in the stack. But in this case, we just declared the variable, we didn't initialize the variable yet. So it actually allocates some piece of memory in the stack, but that particular block of data is empty at this point of time. It does not have a reference to a valid memory in the heap. And this is what we call it as null reference. So at this point, if you try to access the names variable, if you try to call some function within the names variable, in Java or C#, you will get an exception called null reference exception. So now the execution reaches the second line where you are actually initializing the hash map using the new keyword. So at this point, now it actually allocates some section of memory in the heap. It allocates randomly some piece of memory from the heap where it actually have enough opportunity to grow and shrink dynamically. So that's the major difference between the heap and the stack. So once that memory gets allocated, the address of that particular memory will be stored in the stack. Say if the address of this particular memory is 1000 or something, so that will be stored in the stack. And after this line, if you try to declare some other variables, like if you are initializing another hash map, or if you are initializing another array list, or if you try to create an object for another class, then that will be again allocated into some kind of a random section in the heap where you have enough opportunity to grow, and the address of that particular heap address will be stored in the stack. So now this is how the heap memory allocation actually works. And we also know that when the function execution completes, when the variables within the function goes out of the scope, the stack memory actually gets deallocated. And that's exactly what happens in this case as well. When this particular function completes the execution, when the hash map goes out of the scope, whatever memory gets allocated in the stack will be deallocated. So the stack memory will be deallocated, but what about the heap memory? Since heap memory is dynamic and the compiler do not know the size of the heap memory during the compile time, there is no way the heap memory can be deallocated automatically. So that's why it is always the programmer's responsibility to deallocate the heap memory, especially in case of system programming languages like C, C++. It is the programmer's responsibility to deallocate the heap memory. But in case of some high-level programming languages like Java or C#, it actually comes with the runtime, and that runtime actually comes with some garbage collector. So those garbage collector actually takes care of removing the unused memory from the heap. So that's one of the major difference between the stack and the heap, where stack memory gets deallocated automatically, but in case of the heap, it has to be taken care by the programmer or the garbage collector. And especially in the system level programming languages, the heap memory has to be considered very carefully, because if the heap memory is not deallocated properly, at some point of time, if the execution continues, it keeps adding the heap memory, and at some point of time, eventually, you might get out of memory exception as well. So that's why it has to be, the heap memory has to be considered very carefully during the system level programming languages. So in this video, we talked about stack, heap, and how the static memory and dynamic memory gets allocated into stack or heap. So I hope you really find this video useful. Thanks a lot for watching.
Audio Jungle.